So we've already seen this chart before. We filled this out with our formulas, and we kind of did it in a fancier way than I would have liked to, but it helped us get to that definition of a derivative, why we even did the limits in the first place. So let's go back in and remind ourselves, because we're actually going to do these definitions now. We're going to use these on some applications, but we probably don't need to write them as fancy as we did before. So remember we talked about identical twins, where they have the same equation, but they go by two different names. So our first set of identical twins we said was the slope of the secant line. That's what we would call it in geometry. And then the physical application name would be the average rate of change, or average velocity. And then we said both of these things, even though we call them two different things, they have the same equation. So their same equation we said was f of x plus h minus f of x all over x plus h minus x, and then the x's cancel out to just be an h, and oh my gosh, it was so confusing. Let's write it, because we're going to use this now, and we don't need to use that definition of a derivative anymore. Let's call it what it is. It's the slope, and it's just rise over run. In algebra, we said y2 minus y1 over x2 minus x1. We're still in function notation here, but I'm going to write it a little less confusing than last time. We're going to say f of b minus f of a, plug in your 2 points, get their y values and subtract them, over their difference in x's, b minus a. So just the slope formula if you're asked for average rate of change. That's the one we're going to use the most. We don't really do too much with the slope of the secant line, but we do need average rate of change a lot in real life to look at some different patterns, so we'll use that in this class. The other set of identical twins, we're going to do this application first, actually, is the slope of the tangent line. And we have other applications that apply more to what your major is going to be doing with, but I do the slope of the tangent line first, just literally because it's an easier transition into applications than just being like, yeah, let's jump into word problems, because everybody loves those. So even though you don't probably need it for real life, it helps you get ready for those real life problems where we're doing the derivative and then there's more to it. So slope of the tangent line, and in the word problems, this is called instantaneous change. Instantaneous change, or rate of change, or instantaneous velocity. Anything asking for change at an instant is the same steps we would do for the tangent line. For both of those, we don't use the slope formula. We use like the limit as h goes to 0 of f of x plus h minus f of x all over h. That was the crazy long formula that is the derivative. And we're not going to use that formula to find the derivative anymore. We spent all this time learning these shortcut rules. We're going to use those. So if it says tangent line or instantaneous change, you're going to use the derivative, whereas if it says average rate of change, you're going to use the slope formula. So one way that we can differentiate between these two is to visualize it, and that's the other reason why we do the tangent line first, is because we can look at a picture. So I have this website that's linked here. You can open it up on your computer if you want to, but here's what it looks like. And we have a graph, and the green line is the average rate of change, whereas the purple line is the change at an instant. So on this, if we look at a big interval, remember we said if we're driving between 0 and 2 hours, that doesn't tell us exactly how fast we're going at 31 minutes in. It doesn't really tell us anything close. So instead of looking at a big interval for your average rate of change, this green line, it won't even estimate that instantaneous change at that point if you look at too big of an interval. But if instead of looking from 0 to 2 hours, you look from 31 to 32 minutes, if you make your interval smaller, let that h go to 0, the difference between the two x values go smaller, then the average change can really just measure that instantaneous change. They can almost match. So the idea is average change can be over an interval, and it can do a good job at measuring the instantaneous change, but only if you make that interval super small. So you can play around with this if you want to, but this purple line, this instantaneous change, is also called the slope of the tangent line. That's what we're going to find first. And then this green line, instead of just calling it average rate of change, you could also call it the slope of the secant line. But make those 2 points closer, look between 31 and 32 minutes of your driving, and it'll tell you exactly how fast you were going 31 minutes in. So the bigger the interval, the less it measures change at an instant, but the smaller the interval, the closer that it gets.